3 form or a 4 form, it's just a free particle. I just write down a free Lagrangian. It looks like it's perfectly fine, and since it's free, it doesn't create any S matrix. Maybe I'm not subject to this constraint. Well, in general, this is true, but unfortunately, we live in a world with gravity. Okay, so any particle that exists, it can be always neutral, that doesn't couple to anything else, but it always coupled to gravity. And once it couples to gravity, things go bad. So, for example, let's say if you have some higher spin particle, okay, with spin L, and then you couple to 2 gravitons. So let's consider this process with 2 gravitons to 2 spin L particles. So again, we're gluing the 2 3-point vertex. From unitarity, it tells us the 4-point amplitude on the S channel should have this residue. And this is the form of the residue, and you already see that you're in trouble here because you have this L here, which means that if you put more and more L, if the value of L is greater and greater, you're creating more and more poles here that cannot be consistently interpreted. Again, you can do the analysis as I said before, and you'll see that. So maybe I just go a little bit faster. That anything beyond spin 2 cannot be consistently coupled to gravity. Okay, so it's just period. Because you have gravity, there's no way you have any particle that has spin greater than 2.
That's because of your construction in this particular way. Maybe there's some other way to construct.
No, this is just the S matrix.
S matrix, but then you always from 3 points, approach 3-point function, and then try to construct the higher point. Then this is probably a wrong way to go.
No, because again, I'm saying that you have a free particle. Anytime you have a free particle, it's going to minimal couple to gravity. It's just because you have square root of G derivative. That's the propagator. Even though it's free, this does it has nothing to do with the asymmetry over how I write down the Lagrangian. This is just a free Lagrangian, and this amplitude is constructed from the free Lagrangian.
So it's the graviton is doing that.
Exactly, that's my point.
If I have something doesn't couple to graviton, then it's okay.
Yes, but that's the point. Because this is really very interesting. So actually, so I can just jump ahead because for massive waves, it's exactly the same thing. Even though we always say that gravity is weak, it doesn't really matter. But actually, that's exactly the presence of gravity. Exactly why why our world looks this way. Why there are no these higher spin particles cannot exist because of the presence of gravity and the fact that gravity couples to everything. So that means that if you have any higher spin states, unless somehow for some reason it doesn't couple to gravity, then this will violate unitarity. Any higher spin states, once it couples to gravity, it automatically violates unitarity. That's the statement. Yeah.
Only in 4 dimensions?
Yes, this analysis is in 4 dimensions.
But in other dimensions, are there any analysis?
There might be similar. Well, of course, anything below 4 dimensions is covered by 4 dimensions. So I would imagine that after some work, you can make the same statement except for 11 dimensions for 3 forms, which there's a special way you can get out of it. But generically, this will be true because you can think about this. If this can happen in higher dimension, you can always do dimension reduce to 4 dimension. Then you will have something that's reasonable in 4 dimensions.
So where is the composite calculation coming? See, the
exactly.
picture we saw was on higher spin.
Exactly. So this is what I'm going to discuss now.
Okay.
Yeah. But first of all, this is massless, right? So this is not composite. This is a massless particle. So now you want to do, so in order to make my statement really clear, you need to go to massive, and this is where our formalism comes in. So we're going to say that anything that is charged, a fundamental massive particle with spin bigger than 1, if it's charged, it cannot exist. It cannot be fundamental. It has to have, either it's, what do I mean by it's not fundamental? We'll be clear. But also, anything that is bigger than 2, fundamental with massive fundamental spin bigger than 2 massive particle also cannot exist because of gravity. Exactly the same argument here. But actually, what time is it?
It's 55.
I have till 20. Okay. Okay. So let me just go through this. So first of all, we can just reconstruct everything. So I'm just going to use the same way, and we'll see that we'll find that in my approach, you'll see that you can reconstruct everything that you know in field theory textbook. For example, so let's just consider electric coupling. So let's consider massive particle that is charged. It means it couples to photon. So For example, you have a scalar here. So this is a scalar coupled to photon. We already know what the amplitude looks like. So if this is a plus, if this is a plus, and this is the minus helicity, the amplitude in our formalism looks very simple. And if you glue the two together, then you get this residue here, which again has this T channel, but that's fine. We know that what T channel means. The T channel just means that there's going to be another channel that has to be added. And this is the final form that can be deduced from this residue here. And if you do the spin 1/2 and spin 1, you all get the, in our formalism, you get the very nice simple form for the final answer. Now let's go beyond spin 1. And let's go to spin 3/2. So let's write, basically what you can do is you can write down the most general possible three-point interactions involving two spin 3/2 particles and a charged photon, and a photon plus helicity photon and a minus helicity photon here. And then we just glue these two 3-point together. Of course, there's many different forms, so I'm not going to go through all the gluing procedure together. I'm just going to tell you the answer is that in the final answer, you'll get a particular piece of your amplitude that looks like this form. Okay, so these are just some spinor variables. This is the propagator of S minus m squared and u minus m squared. And this form will always exist no matter what kind of 3-point basis you start out with. Now, if you compare this form with all the previous cases, you know something very interesting. Here, for example, you can take mass to 0 and nothing happens. Right? You can consistently turn your mass to 0. Turning mass to 0, what does turning mass to 0 mean? It means that you're looking at this amplitude in high energy, so that means your mass is sufficiently small. But as you see here, you cannot turn this mass to 0. It's just sitting over 1 over m to the 6. And this term will always exist no matter what kind of 3-point amplitude you start with. So in other words, this amplitude does not make sense at arbitrary high energy, because this will diverge. Okay? And the same thing will happen for anything beyond spin 1. So what is this saying? This is saying that a massive higher spin 3/2 that is charged cannot exist because the amplitude that you construct from minimal coupling and what minimal coupling applied to the 4-point interaction will include a term that looks like this, which will blow up. So what is the way out? There's two ways out. One is at sufficient high energies, what the particle that you are scattering is no longer a fundamental particle. In other words, it's a bound state. Okay, because you can because you cannot turn arbitrary tune this mass to 0. This is one possibility. The other possibility is that by analyzing this thing as a single term, this is not the correct thing to do. What do I mean? Let's assume that you have multiple spin 3/2 that is also parameterized along with the same parameter m, with mass that is, for example, integerly spaced, but with this value of m. Then when I'm taking m to 0, all of these states will condense to each other. So I cannot just look at the single amplitude by itself. So if it's that case, then that means that you're looking at something that is, again, not a fundamental particle, but an extended object. And these are the two only known ways, the only ways that we know that you can actually create a spin 3/2 charged particle, which is one is either is a bound state, and two is coming from string theory, which is an extended object. It's one of the excitations. Okay, but you can directly see it from here because if you're looking at it as a single particle, you'll see that minimal coupling forces this term in your 4-point amplitude, which cannot allow you to take m to go to 0.
Does your perturbation parameter 1 over?
Okay, very good. So what is so of course I think many of you will feel like I'm making a statement that seems just too strong to be true, and indeed it is too strong to be true because there's one underlying assumption, which is that the theory is perturbative. Because then I'm allowed to only look at an analytic function that is a rational piece. If the theory is non-perturbative, I'm not allowed to do that. I'm not allowed to say that my S matrix should only have poles, right? Where I can because whenever I'm saying my S matrix is having a pole, that means that I'm having some perturbative parameter to suppress the branch cut, to separate these two terms. For a non-perturbative object, these two things cannot be divided. Okay, so this is really the underlying assumption here. Okay, so this is, and you can do the same analysis for gravity. You just let massive particles couple to gravity, and you again derive the same statement that anything that is beyond spin 2 cannot be fundamental. It must either be a bound state or it must be an extended object. And that is why we don't see that as fundamental particles, because of gravity. Okay, so just, of course, this is the reason that we developed this formula is for a lot of practical use. So this is just some simple slides to show you the practical use. So for example, if you want to compute G minus 2, before I gave this talk, I just looked up in short. So it was a 3-page derivation of G minus 2. But now it's just a 2-line derivation. Of course, assuming that you know how to do integral, that always helps. But basically, all you need to do is, again, you use R variables, and you glue the three minimal coupling together. And this is just multiplying. I mean, I haven't done any algebra anything here. This is just multiply the thing. You have two terms just because you have minus plus and plus minus in this, so you have to sum the two terms. Now already you see that the magnetic moment is coming from here because a scalar will also have this piece. So you're looking at the magnetic moment. So if I isolate the magnetic moment here, then you can see that, I mean, once you're familiar with what these variables actually mean, you immediately see that this actually is just a linear integral. And linear integrals are easy to do. And if you don't know, we can start. This is what we'll talk about this semester. But anyway, just if you do a linear integral, this immediately gives you the G minus 2. Okay, but if you remember what usually how this is done in the QFT textbook, it really involves a lot of gamma matrix identity and so on and so forth. This is basically a one course, one lecture statement. But now it's just very simple. It's very streamlined, and we can do much. Of course, this is the simplest case. You can do WW. So you can, instead of considering electrons, you can consider WW, the magnetic moment for WW. And again, it's just a very streamlined. You just multiply everything together. You isolate these terms, which are just written down here, and you immediately see after, again, it's always going to be a linear integral, so you can just recycle what you did for the electric moment, and then you can get the final answer here. And this is precisely the WW magnetic moment. So there's a lot of practical use in doing things this way. And also, you can think about correlation functions, which let me just spend a few minutes talking about. So usually when we think about correlation functions, we think about operators and you're evaluating its expectation value. But in practice, what we're really doing is we're really measuring the correlation function in momentum space. Why? For example, let's say you're looking at the CMB background. You're computing the thermal fluctuation of the fluctuation of different points in the sky. You're computing its correlation function. What exactly are you measuring? What you're measuring is the photons that are coming from these fluctuations, right? So what you're measuring is in momentum eigenstates. So the real physical observable in most cases is not the position space momentum, position space correlation function, but really the momentum space correlation function. You might say, okay, so what? All I need to do is just try to compute my position space correlation function and do a Fourier transform, and that's it, right? And as we all know, the devil is in the detail. Try to do a Fourier transform on any 3-point functions, because this is a mess. So if you actually really try to do the Fourier transform. But now we can just directly compute this directly without going in position space. Just directly compute it in momentum space. Actually, let me just, because now I remember I wanted to say something here. This is a very important notion that you really want to understand your correlation function in momentum space. Because, for example, there's usually the statement that there are no local operators in gravity. In a theory with gravity, there's never any local operators. And usually the standard way of saying this is because any correlation function is a function of position, right? And gravity is something that is diffeomorphism. That means you can do change in your position. So a local operator is not gauge invariant in the gravity case. That's the usual statement. However, this is unsatisfactory, right? Because we all know gauge symmetry are fake. Right? This is not a real symmetry, right? So there must be a physical way of understanding why correlation functions do not make sense in a theory with gravity. And this is the way you make sense of them. Because when you're writing, if I'm thinking about my correlation function in momentum space, I need to think about it. It must be well defined in all momentum region. However, if you go to arbitrary high energy of your momentum, this function is no longer well defined in gravity, right? Why? Because arbitrary high energy produces black hole. Right? And so this is really why you never have any true local operators in gravity. And that's, if you want to think about why that is true in terms of physical terms, this is why. You really need to think about your correlation function.
Do you talk canonical gravity here?
What?
Do you talk canonical gravity here?
I'm just talking about any gravity that will produce a black hole.
So how do you say operator in gravity?
So you don't have local operators. You only have approximate local
But
operators.
usually gravity cannot be quantized, so how do you say operator? So I just asked whether you use canonical gravity to measure.
Okay, I'm just saying that this observable is not well defined in gravity. That's all I'm saying.
Okay.
Okay, but now we can directly compute these momentum space operators just by, because all of these operators are now really, all of these operators you can, you can think of them as really just massive particles, right? So these are just massive particles with with whatever fundamental particles you have in your theory. And so, for example, you can ask, why is conformal symmetry so constraining on your correlation function, the structure of your correlation function? And that's very simple. That's because when you're computing only massless particles, for conformal theory, you only have massless particles. So only massless particle can appear inside your loop when you're considering correlation functions. And as I've talked about before in the very beginning, one massive, two massless particle is unique. There's a unique answer for that. And so for any conformal theory which only involves massless particle, the correlation function must have a definite structure. That's the momentum space argument of why this is true. And so, for example, now we can just directly write down so this, of course, it's going to be complicated, but that's why you don't want to do Fourier transform. But we have a nice representation for what the momentum space correlator looks like. This is the 3-point correlator. So there's a lot of tensor structures, but again, you can try to reproduce this from Fourier transform. Okay. But the point is that now we can really do things in momentum space. Okay. Okay, now let me just spend the final 15 minutes talking about the second part of what I wanted to talk about today. Is the question of why are particles much smaller than n Planck natural? And then again, I want to answer this from the viewpoint of the S matrix. And of course, the most easiest way to do this is first answer why massless particles are natural. And we all know that in some sense, anything with massless particle can always be understood as a ghost of boson. And this is actually true even for gauge theories. Okay, even for gauge and gravity theory, you can also understand the vector field and the graviton as a ghost of boson. Where what you're breaking is there's a BMS symmetry, or there's a symmetry on your asymptotic infinity where the different vacuums are actually degenerate. So there's some recent discussion about that. But so in principle, we can understand all massless particles as some ghost of boson or some ghostinos. So the question is, how do we know which symmetries are the broken symmetry? Okay, let's say if you accept this fact that all massless particles are ghost of boson, how do you determine what symmetries are being broken? Now, to answer this question, we can always go back to the oldest ghost of boson that we have, which is the ghost of boson associated with the Mexican hat. Okay, so let's go back to the ghost of boson with the Mexican hat. So what does the Mexican hat tell us? What it tells us is that there's a degenerate vacuum, right? When you have degenerate vacuum, what does it mean? It means that if you do physics in any point on this in this vacuum, the physics you have to look the same. That's what degeneracy means, right? You have degenerate vacuum, do physics on either side, perturbative physics, they all have to be the same. So in other words, one of the things that we can do is consider a scattering process. So let's say I consider a scattering process here and a scattering process here. The two have to be give me exactly the same answer at the two different vacuums. However, when you have a degenerate vacuum, that also means that in principle, there must be some generator which can move you from one part of the vacuum moduli to the other part of the vacuum moduli. So in other words, this vacuum theta must correspond to some operator acting on the other vacuum, 0, where theta is now just a constant value. Now, of course, this is exponential, so that means we can expand this exponential down. And so essentially what this is telling us is that since this operator is relating this vacuum to this vacuum is a broken operator, and we know that that any broken operator acts on the vacuum, that gives you the ghost of boson. So that means expanding this down gives you multiple ghost of boson with a constant value. The constant value translated into momentum space means that you have massless particles. So this basically the equivalence of the two S matrix means that anything with a massless ghost of boson, the amplitude involving massless ghost of boson must be 0. And this is the famous Adler 0. Okay, so if we have some particle, if you just want to ask if this massless particle is a Goldstone boson? Simple. You take its momentum to be 0 and see if the S matrix vanishes. If it vanishes, that tells you that this is a Goldstone boson. Now you can also understand this from a current algebra or the usual Ward identity. So we know that the conservation of the current gives you variation of the field. Now, but because this current creates a physical particle, which is a Goldstone boson, so that means on the left-hand side, it depends on whether or not the variation of your field creates a physical field or not that will survive the LSU reduction. If the right-hand side is not a physical field, then it's going to be 0. And this is exactly the case for Adler 0, because we know that in Adler 0, the variation of phi is just a constant, which is not a physical process. Okay, so this is how we know what symmetries are broken. So in the final 10 minutes, I will tell you something about how we know what kind of, when this broken symmetry is a space-time symmetry, how do we know that? So this is associated with soft theorems associated with space-time symmetry. So what is different?
Explain Planck mass, or you want to say the Planck mass, all particles are less than the Planck mass, or what's the relation? You just explain the Goldstone mode.
Right. So first of all, I'm saying that so I want to understand. So it's in that context. So the context is about what is the mechanism to keep particle masses. Mm-hmm. And the first statement is that in all cases where particle are masses, you can always understand it as a Goldstone mode. And now I'm answering the question about how do you know what kind of symmetries are broken? Because Goldstone modes mean you're doing some spontaneous symmetry breaking. So how do you identify what are the symmetries that are being broken? Just without knowing the underlying theory, you want to know what are the symmetries that are really being broken that produces this massless mode. Of course we can do it. Of course we can do it the other way, which is to construct explicit models, break symmetry, and then look at what the signal is. So this way of approaching as with always we're just doing from the very general assumption and then just go and so I'm giving a systematic step of how to identify this broken symmetry that are associated with this mass, with these massless modes. So, but of course you'll think that Goldstone boson is an old story. Why am I still talking about Goldstone boson here? So the story is very different because we've identified certain cases where the Goldstone boson, the soft behavior of Goldstone boson doesn't satisfy the usual case. And let me explain why. So in the usual case, or the case that we learn mostly, for example, the Mexican hat, there, in usual case, the number of global symmetry breaking generators is 1-to-1 correspondence with the number of Goldstone modes. That's the statement, right? You break 3 generators, you have 3 Goldstone modes. That's the usual statement. However, this is actually not true always. If the broken symmetries involve space-time symmetry, this is no longer true. For space-time symmetry breaking, there's a mismatch. So for example, let's consider you have some system which has an extended object, a brain. So the existence of this brain means that you're breaking more than one symmetry. Of course, the existence of this brain means that you're breaking translation symmetry along this direction. But also it means that you're breaking Lorentz symmetry in this rotation plane. There's more than one symmetry generators that are being broken. However, you'll only see one Goldstone mode. Even though there's multiple generators broken, but you only see one Goldstone mode. Why? It's very simple. It's because the symmetry algebra actually has the commutator of translation along this direction with the Lorentz rotation actually produces another broken generator. So in other words, these 2 generators are related by a derivative. So that means that the modes that are created from breaking this generator is related to the mode that is created by this generator, by a derivative. And similarly, if you have conformal symmetry breaking, if you have space-time conformal symmetry, you have exactly the same thing. Derivative on the conformal boost gives you the dilettante, and these 2 are the broken generators. Okay? So in both of these cases, this is no longer true. The 1-to-1 matching is no longer true. And this actually has phenomenological fingerprint. So in the previous case, when we were talking about the usual Goldstone boson, for example, the pion, when you're doing pion physics, or whatever model that you have, for example, let's consider SU2 cross SU2 break down to the diagonal SU2. So here, again, as I mentioned before, if you take the single Goldstone boson to be 0, then your amplitude should vanish. However, if you take 2 Goldstone boson to be 0, you'll find that your amplitude is not 0. You actually get a finite answer with some multiplicative factor which you can derive by current algebra. And essentially you're just using this current algebra here. But an important thing is that here, this actually contains the structure constant of your symmetry. Okay, so at leading order, If you take two Goldstone boson to be zero momentum, you get the final answer with the multiplicator. But that's it. You don't get any new information. You don't get any subleading pieces from the leading piece. Okay, so internal symmetry structures only predict leading soft behavior. There's no universal soft behaviors beyond the leading piece. However, what we want to say here is that this is no longer true for space-time symmetry. And you can use this to pinpoint that whether your theory is actually breaking some hidden space-time symmetry. And as I mentioned before, the reason is very simple. The current that is associated with the broken generators are actually related to each other by a derivative. And if you actually write down what the form of the current is, it is related by, there's always this multiplicative X factor here. So that this is the current for Lorentz rotation and current for translation. This is the current for dilatation and for conformal boost. There's always a relation that relates these two currents with an extra X factor. Now, what is X? Well, in momentum space, X is derivative of P. So the presence of this is actually giving you information about the subleading expansion in your momentum, in your soft momentum. Okay? And more importantly, since this current algebra derivation is true, even if the theory is strongly coupled, or even just along the RG flow, because we're just doing current algebra, we're not assuming perturbative expansion. So this must, whatever I derive from here, this must be true. And indeed, so we worked through this and we found that indeed, whenever you have space-time symmetry breaking, the massless particle, you take the momentum to be zero. Besides the leading soft, which is zero, we already know that it should be zero. There's actually unequivalent prediction for what the subleading soft behavior is, precisely because of this fact that you have mismatch of Goldstone modes. And in this case, so this is for translation symmetry breaking. And also for conformal symmetry breaking, we have a leading piece and also a subleading piece. So we've derived this non-trivial soft leading expansion, and we test it. So first of all, of course, this is very hard to test when you have explicit physical observables. So in some cases we have, for example, we put n equals 4 super EMUs on the Higgs phase, which breaks conformal symmetry. And we were able to compute the one-loop correction and the instanton correction. The one-loop correction is the first perturbative correction. The instanton correction is a non-perturbative correction. And our soft theorems are respected in both cases for the conformal. And for translation soft theorems, we use a DBI action, which is the effective field theory for branes. And indeed, we find that the one-loop ultraviolet divergence also respects the soft theory. And since I'm running out of time, so let me just go through very quickly that you can also derive similar results for broken fermionic spacetime symmetries. And as I mentioned, so now we have an unequivalent statement about what, so if you're underlying the reason that you have this massless particle is because some space-time symmetry is broken, now we predict that you can now look at the low energy amplitude. You expand it in soft momentum to subleading order. You can see whether or not this is true at the subleading order. And let's just say that, for example, we can take, let's say, the string theory answer for gluon scattering. So I'm just taking string theory gluons and pretending that I know nothing. I just have the string theory amplitude. This is a very fun exercise. We can take either the bosonic string or the fermionic string. We can expand in small L4 prime, which means we're getting the string theory effective action at low energy. And then we can dimensionally reduce, since these involve massless vector field, dimensionally reduce will produce massless scalar fields. Good. Now we have a bunch of massless scalar field amplitudes. We can do our tests. So we take the string theory, we expand it low energy, and then we take the two momentum of the scalars to be soft. And exactly we find the soft factor at subleading order. So what does this tell me? This is soft factor associated with breaking translation symmetry. So that means whatever this theory is actually breaking translation symmetry. And why? For anybody who's learned string theory, you know why. Because this is an open string. An open string ends on D branes. So without really learning string theory, you can just take that answer, just do this expansion, do this analysis, you realize that there's an extended object in your theory without ever seeing the extended object, just by looking at this prefactor, this factor here. So in conclusion, we can know what symmetries are being broken using the soft analysis without even really knowing what the true UV theory actually is. So I think it's about time to reach for my conclusion. So in this talk, I hope that at least certain aspects is conveyed. First of all, the presence of long-range forces, which are photons and gravitons, in addition with Lorentz symmetry and unitarity, is actually sufficient to tell us why our world looks that way in many sense. For example, why are the fundamental particles only at these particular spins, and so forth. And in proving this, we introduce a very convenient way to parameterize massive interactions. And we expect that there's going to be many more interesting applications beside the ones that I've just mentioned. And perhaps, hopefully, there will be similar